So in this video, I'm going to explain my thinking behind my development of these parts for the Mass Mover project. So what we've basically got in this CAD file here, I'm trying to model how a vehicle might look. So here's a drawing area. This drawing has a height of 500 millimeters or 50 centimeters, and because the vehicle has to pass underneath a barrier with a height of 50 centimeters, I need to make sure that my vehicle is basically going to be fitting onto this page. I've set the width here to 400 millimeters, and I'm going to be explaining my thinking behind that in a second. So, um, knowing that the vehicle has got to travel at least 5 meters in the shortest time possible, or achieve a distance of 5 meters in the shortest time possible, should I say, I've done some spreadsheet calculations, and I've identified that if we have a wheel diameter of 145 millimeters and a drop height of height spelled height wrong there, excuse me, a drop height of 300 millimeters, then it will cover 5.43 meters total distance. Now the drop height, based on my calculations here, could theoretically extend up to 335 millimeters if I take full advantage of the almost 50 centimeters height, bearing in mind here as well where the let's change tool here for a second, where the top pulley is going to go. So this is where the string is going to run down onto the back axle. In fact, I'm just going to put in a string right now. Okay, so I've added in a grey line there that could represent my pulley string, and I've also made sure as well that as the pulley string, sorry, not the pulley string, the drive string in effect, as the drive string unravels off this back axle, runs up over the pulley and drops down, I'm making sure that the top pulley here is offset slightly so that the string attached to the mass will allow the mass to then fall directly down into the middle of the vehicle. I've compensated here for the size of the mass. I believe these calculations are all correct based on our 1 kilogram hangers. And here we're capturing the mass on this low slung platform. My thinking here is that rather than making a raft of straws, we can work with one of these axle brackets with all these holes in. One of these could be provided and put horizontally and become like a platform for the mass to land on as part of the chassis frame. While I'm looking at this, I think I'm also quickly going to just talk a little bit more here about what's happening with this top pulley. We've got a series of holes here in this axle bracket. This is a universal axle bracket. And if I just identify the size of the hole that this pulley axle is running through, the actual axle itself is 5 millimeters in diameter, and the hole is 5.4, and that's to allow minimum friction as the axle turns in the axle bracket hole. If I put it to 5, of course, it probably would have jammed. Okay, and all these holes here are 5.4 millimeters. I've made this arrangement of pulley holes thinking that I can grab this pulley and I can obviously position it in a range of different locations and also different heights. My feeling here is that often, if the tower frames aren't precisely manufactured, they can be a little bit wonky at the top, and that means that we can then accommodate for slightly wonky tops of towers, and perhaps have the top pulley axle running into this hole, for example, on this front face bracket, and the bracket that's on the second half of the tower that might be slightly wonky, we could then be running it into another hole to make sure that the actual axle itself and the corresponding pulley are held horizontally aligned to the ground floor. So it's difficult to explain that in this side view here. I need to have a really an orthographic projection showing the side here to explain that. But this gives you an element of customization and adjustability depending on how accurate your manufacturing is. Okay, Now then, so we've talked there about the drop distance there. I'm going to go back to my text here. Hopefully, there's no more spelling errors in this. So, I'm trying to make sure here that we've got guaranteed levels of success with the standard wheel size. It should cover at least 5.43 meters, even if we're not getting this full drop distance of 335 millimeters. An extra bracket has been developed that will allow the use of a wheel down to a diameter of 70 millimeters. Um, and that will allow the vehicle to be powered over a distance of 2.62 meters. So this distance of 5.43 earlier is powered traveling. The mass is still falling. The vehicle is still accelerating through that potential energy being converted into kinetic energy. And after that distance of 5.43 meters, the mass will then land in the capture device, the net, or the platform at the bottom of the mass mover, and the vehicle will then continue to travel under its momentum, basically freewheel. So with a diameter of 70 millimeters on the wheel, we get a powered distance of 2.62 meters. I've got that as the theoretical smallest we could take the wheel. In fact, actually, no, thinking about this, I could go even smaller. Look, I could take the wheel down to, I don't know, I'm just going to try and guess a value here. Let me see, that's going to be 15. That's going to be 37, 27, 22.5. Let's try that. Yeah, look, I could have a wheel. There we are. Let's just make sure I put my line back to fine there. I could have a wheel coming in like that, but I haven't done the calculations for how far that would travel. And I think making it that small would potentially lead to difficulties. But here with 70 millimeters, I'm just going to undo that there. Yeah, with 70 millimeters diameter wheel, 2.62 meters, we're traveling just over half the distance under power, or slightly more, a bit more if we get the full drop distance. And so therefore, my thinking is we have a range of possible permissible wheel sizes from 70 up to 145. And I'm suggesting here that the default we provide as the option for people that can't do the calculations is 145 millimeters. For those people that can, for those designers that can, they can then provide us with precise wheel diameters, and we can and the CAD files appropriately created, and we can then manufacture those for those students. Okay, you'll notice here there's a whole bunch of holes. That's so that for different size wheels, we can then position them in the axle bracket such that the bottom of the axle bracket is relatively close to the ground surface here, the ground floor, and ground floor. Doesn't quite what is it? The surface of the floor. And here in this example, I've got it raised one centimeter, so that's a wee bit tight. I'm a little bit worried here about when the mass hits the collection platform at the bottom here, that it could bottom out and cause a problem. So my thinking here is that what I'll probably want to do, and the dimensioning of this drawing aren't going to be quite right, but I would want to have this kind of collection raft kind of sitting somewhere on the top like that. So, this is just very quickly hashed together, but if I can just do that, that's like the collection raft, and it's sitting on top. So it gives we don't want anything really coming down below this axle bracket, because we've literally got that 1 centimeter variation. So just something to consider there. Okay, what else have I got in this model? So I've made this axle bracket 75 by 75. As I've already explained here, for the top axle bracket, I've got these small holes for the 5mm dowel. And for the bottom axle bracket, I've got these 8 millimeter diameter holes. In fact, they are 8.4. Oh, 8.5, sorry, excuse me. Oh, that's 8.4, that's 8.5. Okay. That's 8.5. Okay, I'm gonna have to fix up in my model. Okay, got I spotted that one. Anyway, make them 8.4. So again, it's supporting the axle nicely, but there's a bit of tolerance to allow that axle to turn more freely. I've got them at different heights, and I've also got them on both sides as well, because historically I found that students don't really look very carefully when they're gluing these in, and quite often they're glued in at the wrong position, and it really messes up their vehicles. So this gives them a 50-50 chance of, if they're not concentrating, at least getting these axle brackets correctly positioned. And this is something to take heed of. I've also inserted these little markings every 5 millimeters. I've got every 10 millimeters. I've got a big indicator, and then every 5 millimeters a small indicator. So I'm just going to explain the thinking behind this. We have got, and I've got Fred here to help me on this one. We are now working with potentially these smaller art straws. Sorry, these smaller art straws, should I say. These are the original size, which I think are just about 40 centimeters long. These smaller ones are coming in at 18.5. You probably can't see that very well because of the lighting, but that says there we are, 18.5 or 185 millimeters. And I'm thinking, if we're going to be working with these art straws, how can we kind of, develop our designs to accommodate that? So what I've got in here is an art straw. Let's just get the right size here, which is coming in at 185 millimeters. And I've made it so that these axle brackets are glued in such a way that the art straw doesn't have to go right to the end. The art straw only passes halfway over the axle bracket. And to make sure that we get consistency in the precision manufacturing of the chassis, because that is so important in making sure that the two axles are parallel and the vehicle goes in a straight line. If we don't cut these 185 millimeter shorter art straws, we leave them full length, and we also perhaps double check that they are all the same length, and we use these markings on the axle brackets. Then the idea is we can really, try and ramp up the accuracy of our chassis, improve the straight line that they travel in. We don't want the axle brackets to have misaligned or not parallel, which would cause the vehicle to turn. And if there does happen to be a need for just adjusting where we glue the art straw onto these axle brackets, we can use these little indicators to then control that positioning. So it's like a little calibration feature. Okay, so there we go. As a result, it means that the actual distance from the axle center to axle center of these wheels is 235 millimeters. It means that the actual length of the chassis here is coming in. Whoops, that is wrong. It is coming in here at 260 millimeters, or 26 centimeters for the actual length of the chassis. If we have a look here at the total length of the vehicle with the wheels included, it's coming in at 380. And if I think here about the fact that we're going to have to print off the design for the tower, why did I specify the width here to be 400 millimeters or 40 centimeters? Well, if I actually map out how big the tower will be, so let's now just go from this top axle bracket to the, let's just have a look here. I'm going to come out here and zoom in a little bit, and I'm going to come to about there, which is just 5 millimeters below that lower axle bracket. Oh, that is the wrong dimension tool. I want the vertical dimension tool. So I want to go from there to there. This is coming in at 415. In fact, look, I've already got a measurement of there of 420, okay, with a little bit of tolerance. And now and I know that this distance for the distance of the chassis, the length of the chassis is 260. So we've got 420 height, 260 in width. Well, if I go to the layout options here, then you'll notice here that standard A3 is 420 by 297. So if I work with these dimensions and I make my tower, 420 by 260 maximum, it will fit onto a sheet of A3 paper. That would mean that I would have to start a new CAD file here, setup, drawing, layout, A3, in portrait. I personally would do the whole 5mm grid thing, pale blue, lines, and I've also found it incredibly useful as well to set the step spacing to 2.5. All my calculations on this other document have been in 2.5, and now I can effectively, let's just show this right now, I can, select these axle brackets. Let's copy them. Let's bring them in. Bring that down to there. And I can see here that perhaps just a little bit further, 5 millimeters further down. Yep, I'm now in a situation where I can build my tower on here. And when we print this, perhaps the print margins will stop the extreme elements of the tower framework being printed, but there'll be enough information there for, I think, the students to be successful. Good. So I'm hoping that's all making sense. Voila, it's been a bit of a long video, 15 minutes. I'll stop there.